We're going to start chapter 10, which is atomic theory, the modern atomic theory, and some more information about the periodic table. Okay, one of the things to remember about the electrons is the electrons travel in orbits, in patterns, okay? And they can actually measure those by the amount of energy they give off. They give the energy off in wavelengths, and wavelengths in this very small area, invisible light, what we can see, is certain colors. So if they can measure the wavelength, they can measure the color, they can tell you more about those electrons. And in this chapter, we're going to talk about a lot about electrons and their configurations and stuff. It's important to know where electrons are, because the more you know about the electrons, the easier it is to make compounds, because that's where it happens. It's with the electrons. The electrons move around or they share or whatever. When you talk about protons and neutrons, they stay in the nucleus and they're not involved in that part of it. So that's why it's important to understand where electrons are, okay? Um, when we look at these electrons, the energy given off, they move in two different ways. They move in little packets called photons, and they also, like this up here, they move in waves, okay? So you can get a line spectrum for an element. And the fancy machines, like if you watch the forensic shows like the mass spectrometer and all that, that's what these things do. They read the wavelengths of light given off, and then they can tell you what elements is, because they've run enough elements through, so they just compare them. So if you ran pure hydrogen through one of those machines, what you would get is it would leave marks at these spots, and then you could compare them to a database where they're already in there, and it would say, oh, that's hydrogen. Okay, so the line spectrum indicates the specific wavelengths or the frequency of the lights, and it gives it a unique. So every element has a unique spectrum. And again, there's a database that's already been set up. So then when you put something in there and you don't know what it is, the machine says, oh, it has hydrogen and carbon and whatever, based on their spectrums that they give off. And again, every element's different. Okay, so how do you explain these different lines? Why isn't it just one continuous line, or why do you have these characteristic lines? Well, again, that deals with Bohr. Remember, Bohr is the one that came up with the idea that we have the nucleus with the protons and the neutrons, and then the electrons travel in orbits. They don't hang out in between. Okay, so they're either here or here or here. If you go back here, see, we got orbits. One here, one here, one here, one here. So that's kind of where they got, after they did the line spectrums and they realized, yeah, they're in these, they're actually called energy levels, okay? But they don't travel in between. They're in the energy level. That's why you get the lines, okay? And again, the electrons go in these fixed patterns, all right? That's their distance that they travel, okay? You won't find them in between, okay? This down here, this is the lowest energy levels, called its ground state, and that's where electrons want to be. They want to be in this one, and when this one's full, then they'll move up to this one. When this one's full, they'll move up to this one. They will not fill this one until this one's full. That's the way electrons roll, okay? So he said that there's a certain amount of energy in these orbits, and it's a fixed unit, okay? And so he said, again, he's the one that said they travel in these energy levels, these orbits, and they don't travel in between. And from all the work they do now, he was spot on, okay? Now, what happens now when, this is the ground state, this is low energy where they'll be. If you excite them, and the way you excite them is you give them energy, okay? You can do this easily. Has anybody ever done a flame test? You've done this. What you can do is you can take that element and you can add energy to it. You can heat it, and it'll absorb the energy and it'll jump up to the next level, even though it's not normally supposed to be there. But because you added energy to it, it jumps up. All right, let's say we got this, it's supposed to be here, okay? When it goes back down to where it's supposed to be, it releases that energy. So first it absorbs the energy and it jumps up to a higher level. Once it gets up there, then it's like, okay, I'll stay up here a little, but I'm not really supposed to be here, so I better go back down to where I go. When it goes back down, it releases energy, and the energy that it releases is a specific wavelength. If you've ever done a flame test, when you put different elements in, you get different colors. If you want to see a beautiful flame test, think of the 4th of July. Okay, those are ginormous flame tests. All those different colors are given off because of different elements. They give off different wavelengths. So you excite them when you shoot them off, and then when they go back down to their ground state, they give off their color. Each element gives off a characteristic color, a characteristic wavelength, and that's why they're different colors. Okay, so when the atom emits energy, when it goes back down to where it's supposed to be, that's a certain color, and that's why we get, like I said, when you do flame tests, when you put elements in a flame, they give off different colors. That's why when you shoot off fireworks, you got different colors. It depends on what elements are in there. Okay, so the ground state is where they should be. That's what they call their lowest energy level. Okay, each line spectrum corresponds to an energy level. So when I showed you that one of hydrogen had, I think, 4, those would be different energy levels. Okay, when you add energy, they jump up to a higher level. But again, that's not a normal place for them to hang out. So they're going to go back to where they belong. When they go back, then they give off the energy, and that's when you get the spectrums. And again, they're a certain wavelength. Every wavelength has a different color. Okay, the color of light emitted depends on the gap between those energy levels. Okay, so whatever their wavelength is, that's the color they're going to give off. Blues are more toward the bottom. I think reds are more toward the end. Higher levels, I mean, not end. Okay, so it worked out really good to explain Bohr's his idea of these energy levels where you find the electrons. Okay, it worked good for smaller elements, but sometimes you had some issues when you had larger ones. Again, when you have inner, like the transition elements and stuff, it didn't work as well, but it works really good for the smaller elements. Okay, but again, we got the idea that electrons travel in orbits. They have certain places, certain spots where you'll find them. Okay, so what they started to do, they kind of added on to Bohr. Instead of saying they're in these energy levels where it's just like an orbit, they started talking about orbitals. And an orbital is a place where you find 2 electrons. Okay, in Bohr's, he had an energy level where you'd find 8. Well, in one of his energy levels, there's actually 4 orbitals. Okay, so orbitals are more specific. When you, like I said, Bohr got it started, but it's more specific than that, and that's why they have orbitals. Excuse me. Okay, let's say we're trying to find the electrons in hydrogen, and they did a probability, and you can see they're more probable to be in this area than out here. Excuse me. Okay, so the orbital for a hydrogen atom would be this area. That's where you're more likely to find your electrons. Okay, so again, his idea was okay up to a certain point, but because we have this wave function and we have these photon functions, and again, we can be more accurate with orbitals than we can with Bohr's idea of just an energy level holding 8. Okay, so we use what they call quantum mechanics. It sounds really like we're really brilliant, but really what it is looking at the energy levels of the atom. And again, I'll show you how to figure these out. They have different levels, they have different numbers to describe them. Okay, we have what they call quantum numbers. There's 4 quantum numbers to describe where the orbitals are. And again, an orbital is a place where you find electrons. Okay, the first energy level, the first quantum number, excuse me, is called the principal energy level or principal quantum number. It's whatever row they are on the periodic table. So it's a whole number, and it goes from 1 to 7 because we have 7 periods in the periodic table. Okay, so it tells you how far they are from the distance. If it's 1, it's really close. I mean the nucleus, not the. If it's 1, it's really close to the nucleus. If it's 2, it's a little farther. If it's 7, it's really far away from the nucleus. And the farther they are from the nucleus, the less influence the nucleus has on them. So it's easier to form compounds with one that's in the 6, 7 range than it is when one that's in the 1 and 2 range. Okay, so each energy level then is divided into sublevels. So the first quantum number is just, is it in row 1, 2, 3, 4, 5, 6, or 7? Okay, they have the second one, the principal quantum number, again, is what row they're in, but the second quantum number actually kind of describes the shape of the orbital. And they have placed it in numbers, but the old school, and that's what we'll stick with because it helps you better describe them, is that they have what they call, the shape is either an S, P, D, or an F. Okay, and remember, each orbital holds 2 electrons. So if you look at the first row on the periodic table, there's only 2 elements. There's hydrogen and helium. So there's only one orbital, a 1 because that's the first row, and S because that's the orbital. When you're doing the letters, they go in order. First you have an S, then you have a P, then you have a D, then you have an F. The 1 only has an S. The 2 has an S and a P, it has 2. The 3 has an S, P, and a D, it has 3. The 4 has an S, P, D, and F, it has 4. There is no 5 and 6 for the shapes, so we only go up to the 4. But again, I'll show you how to do these in a little bit. Okay, when you're talking about an S orbital, it's spherical. In this shape, I will find 2 electrons. Okay, and this is actually the first two columns, the alkali metals and the alkali earth metals. These are all S. So if you're in the 4th row, you're in the 4S. If you're in the 7th row, you're in the 7S. Okay, so you take the principal quantum number, and then those 2 groups are S's. Okay, the probability of finding those 2 electrons is in that area is 90%. So that's pretty high. Okay, so how many electrons can fit into an orbital? There's a couple rules we'll follow. One's called the Pauli exclusion principle, and what it says is an atomic orbital can only hold 2 electrons. And the reason why it can only hold 2 is electrons, when they're spinning, they're kind of like a magnet. They have basically poles, and if you put one in spinning one way and you put the next one in spinning the same way, they're like a magnet. You know how you put the 2 norths together and they push each other apart, but if you put the north and the south, they stick together. Okay, that's kind of the way electrons are. If one's spinning one way, the other one has to come in and spin the other way. Then they'll stay in the orbital, but if they're spinning the same way, they'll push each other up. Okay, so when you look at the next orbital for the shape, now I'm talking about the second one. Okay, it's actually got a different name. It's the angular momentum, which I'm not really sure about why they call it that, but it's really the shape. And the second quantum number is number 2, has 2 different kinds. It has S's and it has P's. Okay, the P's, I'll show you shape. They're kind of like a bowling pin. They're described as dumbbell shaped. Okay, here's what they look like. Okay, so the 2P, and again, the reason why there's 3 of them, if you look on your periodic table, the S was the first 2 columns, and then you skip over, like once you get past, you've got lithium and you've got boron, then you go, or beryllium, you go over to boron. And boron, if you go from boron to the end, there's 6 elements. Okay, those 6 elements, well, there's 2 in each orbital. So there's 2 here, 2 here, 2 here, and then you'll have your 6. So this is the second quantum number is P. And like I said, they're kind of dumbbell shaped, kind of, even bowling pin, whatever. So those would all be. And the third quantum number is X, Y, and Z. The third quantum number tells you what axis it's on, where their orientation is. So when you're doing quantum numbers, you have 1, 2, 3, 4, 5. That's the first one. That's called the principal quantum number. That tells you what level they're at. Okay. The second is S, P, D, or F. That tells you the shape. And the third one is the what axis they're on, X, Y, Z. I'll show you some D's, and they get crazy. And we don't really write them down because you got to write enough when you do these notations. And again, I'll show you that in a bit. So we have X, Y, and Z. And then the last one is called the spin quantum number, and it's either spinning one way or the other way. They mark it as +1/2 or -1/2. But again, I showed you the arrow. I think it was here. I didn't. Nope, I didn't. Anyway, they spin one way or the other way. Yeah, here or here, up or down. And that would be the third one, okay? So 6 total electrons here because, again, every orbital has 2 electrons, 2, 4, 6, okay? And a p orbital has 2 lobes. A lot of people call them dumbbell shaped, okay? So the principal quantum number, again, is 3. So now we have 3 different orbitals. We have the S, which we already talked about, the spherical, P, which are the dumbbell shaped, and D. And D are 4-lobed. Again, there's only 2 electrons, 2 electrons. This one to me looks like a double baby pacifier. I don't know. You guys will have to decide. And you can see why we don't always write down the orientation because they get kind of crazy. Okay. So D would be the 4 lobes. Okay. 10 electrons, again, because there's 5 of them, 2 in each. Okay. This is the level. And again, I'm going to show you this. This will be easier for me to show you on a periodic table. I'm trying to think. So if I'm trying to figure out the maximum level in the 4D, well, D has 10. S has 2, P has 6. And that's where we're going to quit.